All right, well, we're very privileged today to have our lunchtime speaker be Robinson Pino. I've known Robinson probably for about 5 years. He is an expert in the neuromorphic computing area. He's worked in the field for a number of years. He's done some groundbreaking research in the area and is truly somebody who you want as a program manager over an area like this. Robinson is currently a program manager. He recently was the acting division director for the Department of Energy's Advanced Scientific Computing Research, OSCAR. He manages a basic research and development portfolio that focuses on revolutionary and innovative efforts to advance the nation's leadership in high-performance computing and applications that will continue to enable leadership through exascale computing and beyond. Robinson has a PhD and a master's degree in electrical engineering from Rensselaer Polytechnic and a BS in electrical engineering from the City College of New York. Please welcome Robinson Pino.
Thank you. All right, well, good afternoon, everyone. And it is a pleasure for me to be here talking to you about what we in DOE are doing to support the research and development that you're working on. And one of the things that I've been working for several years now is in supporting microelectronics within the Office of Science, and which, believe it or not, is an area that we haven't supported for some time, maybe over a decade. However, our national laboratories have done a lot of work in microelectronics over many years. So today I'm going to talk about our interest in supporting an initiative in microelectronics research and development. And many of you may not know a lot about the Department of Energy. We're very well known through our national laboratories, but the Department of Energy has multiple areas that we focus on. One of them is obviously energy, which is what we call the applied offices, and we have the basic R&D, which is in the Office of Science, and we have also within DOE the Nuclear Security, NNSA, the National Nuclear Security Administration. And in terms of the technologies that we have supported for many years and are beginning to support that relate to microelectronics, many of you probably know about the supercomputers that we have, the large scientific user facilities that we have. For the past 2 years, we started funding research on quantum, neuromorphic, and we've been very focused on getting to exascale. And many of you have seen probably the press releases of the 2 exascale systems that have been announced. And one of them is going to be right here at Oak Ridge National Laboratory, which is the Frontier system, which we're looking forward to it. There's a lot of great scientific research results that we've been able to accomplish with the current system, which is Summit. And so the future for large-scale simulation looks very promising. Within the Office of Science, we fund very large scale user facilities and experiments, and that's something that we would like to leverage as we look at microelectronics in particular. In the Office of Science, we are responsible for the stewardship of 10 national laboratories that have various scientific missions. And when we look at why we would be interested in the area of microelectronics, as many of you know, there is a lot of areas of application that require new types of sensors, processors. We obviously are reaching the ends of, well, I said potentially reaching the ends of CMOS, scaling in silicon. However, we've been saying that for probably a decade, and maybe silicon could make it, but there are clearly some challenges. And however, the opportunity space to apply all these technologies continues to grow. Historically, we've worked with industry to advance microelectronics technologies, and here's some example of those. And recently, we announced our Quantum Information Science and Technology Initiative that we started last year, where we are funding research and test beds on quantum computing, quantum networking. And today, a lot of the technologies that we use within our scientific user facilities depend on microelectronics, and it depends on state-of-the-art microelectronics, not only within our supercomputers, but on the sensors that we use in our scientific user facilities. Within DOE, overall, there's actually funding and investments within the applied offices that is helping propel microelectronics. And given the nature of the applied focus of these activities, we believe that there is an opportunity for basic research opportunities. Like I said before, we have multiple large-scale scientific user facilities across the United States, and support some Large Hadron Collider in Europe. And so we believe that we could have a contribution and impact in this area. So last year, we had a basic research needs for microelectronics, where we had a lot of many people from the scientific community to get together and think about ways in which the Office of Science could contribute to enable R&D in microelectronics. Today, we have a brochure that is published in our website, and hopefully soon there'll be a full report that will be published. And through this workshop, through many other interagency activities, for several years now, we have been looking at the opportunities for new types of R&D that enable our continued leadership in microelectronics, in the semiconductor industry, and it is also part of the national security strategy for the nation. So it is a very important activity for the nation as a whole. And so last week, we announced a request for information on a basic research initiative for microelectronics within the DOE Office of Science. And the areas of interest that. that we are seeking your input on they're quite broad. And in terms of collaborations, partnerships, what could be the role of our current national laboratories? How could we craft such a program? And for you, this is an opportunity to give us input as to how you could envision a basic research program in the area of microelectronics. This activity is currently supported by 3 offices within the Office of Science, which is my office, the Advanced Scientific Computing Research, Basic Energy Sciences, Fusion Energy Sciences, and High Energy Physics. So it's actually four offices. And so we're looking for your input as to how this program could look. So one question that I get often is what kind of projects, what kind of ideas would be interested on. And so the input that we're interested in receiving is at a programmatic level that could enable specific projects or facilities to be supported. And so all your input, both from the private sector or academia or the national laboratories, is very welcome. And this is an opportunity for you and basically anybody to have a say on how a potential program could look like. And the areas that we have highlighted, they're broad, and they're not, just as an example, they're not exclusively limiting. But one of the things that I would like to emphasize is that we would like to consider the whole stack of microelectronics that would go from materials, devices, circuits, architecture, algorithms, tools for fabrication, synthesis, characterization. So it's pretty much the whole ecosystem for microelectronics. And applications can be an important driver to justify the need. And these are some themes, again as an example, because there are a lot of emerging areas that you may have overlooked, such as memory and reconfigurable systems, AI, edge computing, sensors, IoT. And the new word that I've been hearing is EOT, the Internet of Everything, something like that. Power electronics, the energy grid, energy of computation, and packaging. So it is quite broad. And so the goal is to support long-term basic R&D. One of the things that we have highlighted as things that we're not interested in receiving information about is on trusted boundaries and fabs. Because as I was looking at the slides I gave out last year, and last year we had an RFI from the Department of Defense that basically dealt with seeking information for trusted foundries and foundry access for the U.S. government. And so that one is obviously included because we want to focus on the basic R&D. And so I want to emphasize that this RFI is a very important process to help us take your input, but also to gauge the need for the Department of Energy to begin basic research activities in this area. So with that, I want to leave plenty of time for any of your questions that you might have, and I'll be very happy to answer those now or throughout the conference. So thank you.
All right, does anybody have any questions?
For instance, do you think that you plan to collaborate closer with semiconductor industry? Is this something that is independent of the industry side and it's just focusing on basic ideas? How do you think it's going to play out?
Well, that's a great question. Thanks a lot. So the role from industry is very important because at the end of the day, industry is the one who's going to fabricate the next generation of microelectronics. So historically, and one of the reasons why microelectronics have not been funded for many years is because industry has done a great job in maintaining leadership in the area of microelectronics. However, as we've seen the challenges from the bigger nodes to the smaller nodes, and the limitations, the power walls, the frequency walls, and all this stuff, there is an opportunity for innovation, for doing new things. So input from industry, I think, is very important in how industry could, in general, benefit from such a program as an opportunity for performing high-risk basic research, and ultimately that is translatable to industry. Now, industry also has a lot of collaborations, not only with the government, but with academia. And there is also the academic component of basic research and how it can be structured so that it is effective. So yes, so the role, so right now the opportunity is for any one of you to provide us input as to what that role could it be. So we don't have a set role per se, but we're welcoming input about what that role could be, how could it be executed, how it could be evaluated, and what would it need in terms of support from us to be effective. Does that answer the question? Yes.
Although, as you say, the DOE hasn't had a prominent role in funding microelectronics research for a time, organizations like the SRC, the Semiconductor Research Corporation, have.
Yes.
And they've been doing things for many decades with novel devices and materials, spintronics and graphene and so on. Can you comment on, whether those are the kinds of ideas you're looking for, and also on how you might distinguish yourself from what the SRC has been trying to do?
So that is really good. So when we think about the SRC work, and I do attend the SRC review and the NCORP review, my perception is that a lot of the research being performed is performed at various research centers that is quite independent from one another. Some of it is supported by industry, performed jointly with industry. but it seems to be kind of in its own trajectory. So the way I would like to think about in the sense of how we establish scientific user facilities, how can we have a more coherent and open approach to performing those types of research. So I would expect significant collaboration and synergy with what the SRC is doing. And we are expecting input from SRC. We've talked to them about it. So yeah, does that answer the question? Yes.
Comments on other government agencies' microelectronic efforts at this right now. Are you looking for collaborations for new types of initiatives that might be done in collaboration with other government agencies?
So in terms of collaborations, yes. And so we're not doing this in a vacuum. We've actually been working through the interagency process in terms of the initiatives that the several agencies are taking. And so we're taking a leadership role in the R&D. Would we support collaborations? Absolutely, absolutely. But in terms of the basic R&D, we want to take a long-term view and horizon in terms of how we can enable the innovation and the innovation infrastructure so that the work can take place and it can have some sustainability and endurance, and it won't be like single type projects that could be big in volume in the funding available, but they could die at the end after a certain amount of years. So how could we extend that so that innovation can be sustained? And in terms of the topics, in terms of the areas, I mean, it's very broad. I mean, we're even including tools, like new tools for synthesis and fabrication and characterization. What is the next generation? Is there something beyond EUV? Is there new types of materials, photoresist, mask, EDA tools? So everything is within scope. And one of the advantages that we need to appreciate within the Department of Energy Office of Science is that when we normally start programs, they have a significant long-term horizon in terms of the sustainability and support of those projects. Well, I wouldn't say projects, programs. That within those programs, there'll be big and small projects and plenty of competition for people with great ideas to be able to mature them. And we have a lot of experience not only doing and those large facilities and projects, and in my office in particular, in terms of how we work with academia and industry to ensure that we maintain leadership within supercomputing. And one of the things that I want to highlight is that to make a significant impact in microelectronics is not cheap. And so when you think about the input that you want to provide, if you have a sense of the cost of doing business, that would be also some very valuable input.
Any other questions? Well, I have one, Robinson. So if you get the program funded and you carry forward, what would you see in 5 years or 10 years? What's sort of the vision for what this could look like?
So the vision for it would be potential new facilities for performing collaborative research that could expand multiple agencies with various interests in microelectronics. Also, very strong partnerships, potential partnerships with industry, states, potential consortiums that could help us continue our leadership in microelectronics.
You alluded to the issue of sustained funding going
Yes.
into the future. And I wonder if you can comment on the kind of mixtures of sustainment versus the typical need to sunrise and sunset various kinds of research investments. So, for example, NSF has a way that you can do a large consortium initiative where you have a lead university and a number of others. There's typically substantial funding, but it's also time limited to 5 years. So that's kind of a modality of being able to say, yes, we recognize that we need to have not just one research proposal funded at a time, but have something that's more sustained, but it's also time limited versus something saying, hey, we're going to spin up a new facility within a national lab that's going to be there for 30 years. So kind of where do you see what you're hoping for this initiative to be in that spectrum of permanence versus time limited?
So the way we normally run scientific user facilities is on a semi-permanent time horizon. The way we, in particular, like one good example right now is within my office of getting to exascale. So our mission of leadership computing doesn't end when we get to exascale. So exascale is just a goal that hopefully we will reach by 2021. But the mission continues. And within exascale, as an example, we started a very large project, the exascale computing project, which is quite significant in value. That for several years, the amount spent in the project, it will be a few $1 billion on one project. But the mission will continue. And after the exascale systems that have been announced are installed, and we're doing great science on it, we're currently thinking about the new areas of research that will ensure that we will continue to have leadership in computing, for example. And so microelectronics, this initiative, will be part of that vision. Yeah. So long-term horizon, and with our facilities, like here we have the installation neutron source. At Brookhaven, we have a very bright light source that is now on a second generation. So these are multi-decade missions that will continue as long as there is a need to have it and to continue to move on and continue moving. So yes, it's quite long term.
So you're talking right now in terms of like your looking for input from other people, and you're saying like basically everything's on the table in terms of microelectronics. But after you've gotten the input, do you have like a general idea of like how narrow or wide your scope is going to be, or are you waiting for the input to come in before you determine that?
Well, the actual scope, it will obviously be determined by appropriations by Congress. Currently, the administration's request to Congress in the area of microelectronics, for the Office of Science in particular, is about $25 million to begin efforts, which is comparable to how we start most of our big initiatives. Our quantum computing initiative, I think, it began with about $14 or $16 million, and it's currently about $300 million worth of investment. The exascale initiative began about 8 to 10 years ago with very small investments that grew up to several hundred million per year. Today's budget. So we normally start small, and then there is a ramp up, and so right now the input, the significance of the input is to seek input for ideas, not only for ideas about the type of program it could be, but also to gauge the need. And so if we get good responses saying that there is really a need for this type of basic research program at a national level, that also help us to justify the case to the appropriate. So the input that we're seeking is very important.
What are the likely goals in terms of national interests versus international competition and cooperation? And we all know where, for example, the main foundries are now, so there's both a cooperative international aspect and there's also a competitive international aspect, like who is the biggest supercomputers. Where do you want to land?
Well, within DOE and the national laboratories, we actually have quite a number of international collaborations. And the main driver for R&D is well, there are multiple drivers, but the main one is when we look at the state of the art of microelectronics and how hard it has been for industry to continue performing scaling. When we have, the number of state-of-the-art fabs shrinking to, I think there are 4 at the very end, at the very leading end. So I mean, because the cost of doing business to get the next generation of fab is so astronomical. Well, the question is it even possible to go beyond the state of the art, which basically becomes a basic research question. And so that's where we see our primary role. So within the U.S., we the Office of Science, we're the largest funder of basic research in the physical sciences. And so it is within our mission to potentially help you know, help the community, build the community, so that we can move on and find those breakthroughs that will enable our continued, continued innovation in the area of microelectronics. So it is very broad, and we'll still continue to have international collaborations. But at the basic research, the important bit is, could we find a breakthrough, a solution that will take us forward? So that is the main driver.
All right, we may have time for one more question. Okay, last question. Ellen, you're up. Yeah.
Thank you. My question actually is, how do you value the collaborations at the information acquisition stage? So the collaborations, for instance, between universities, with industries, with labs, and is it encouraged, or it's more like a problem description is necessary at this stage?
So that is a good question. So in theory, anybody can make in practice, anybody could make a submission. If there is a consortium, a group of individuals who may want to think of a potential program idea, that would be great. And so either or is acceptable. And because the challenge covers so many sectors, not just the government, industry, or academia, but it covers all of it, and big industry and small industry as well. And each one has a different stake, a different mission, a different need. And so, ideally having if somebody could think of a great way to execute a national level initiative that would help everybody, the more comprehensive it is, the better for us. And so we're looking to getting all the input. If you read closely at the RFI, I believe most of the input is going to be publicly available. So any inputs that come in will be publicly available. Obviously, there is a clause in terms of proprietary information. However, we're not looking forward for ideas as to which specific projects to fund. So I wouldn't expect the need to have proprietary information in the RFI, because what we're talking about is, if we were to have a major initiative that would serve many communities, and provide opportunity for innovation to many, what that could look like, how it could be governed, how it could be executed, how it could be reviewed. And the areas that we point to, they're broad, and the goal is to cover as much as possible the area of microelectronics.
All right, well, let's thank Robinson again.
Thank you.